take a moment to go through the practice exam that you have for Module 3. So hopefully you agree with me that this is kind of a fun exam and not really a super difficult exam. It's a little bit on the easy side, but it's very important you try the practice exam before you go through this video. Otherwise, you may not get a clear idea of what you don't know and what you do know prior to seeing these solutions. So if you have not already tried the practice exam, please go and take a moment to try it out before you watch the rest of the video. Otherwise, I'll start here with question number 1 on the practice exam for Module 3. Here we go. Question 1. Adjusted R-squared is sometimes a more helpful model selection criterion. Okay, well, we do use adjusted R-squared in the same way that we use regular R-squared in order to discern what proportion of the variation in our data something like a linear model might be able to explain away. And it says adjusted R-squared is sometimes a more helpful model selection criterion than regular R-squared because it includes a degrees of freedom adjustment. Well, yes, absolutely. Seems like an easy warm-up question. The difference between adjusted R-squared and regular R-squared is this one has a degrees of freedom adjustment, which means that it's not always going to choose the largest and most complicated regression model. If the model is very large relative to a small sample size, adjusted R-squared is going to start to get worse, and maybe we'll perceive that as something of a warning that we're overfitting the data with a big model when we shouldn't be doing that. The formula below, question 2, the formula below is called mean squared error. Now I love mean squared error because it's one of my favorite class of statistics. Statistics where the formula for the thing is in the name of the thing. So if it's mean squared error, I should be looking for the average of the squared errors. So I see some squared errors here. I've got yi minus yi hat. Yi hat is the fitted value from some sort of a model. It could be many different things, but yi hat is a little bit more complicated than, say, y bar, which would show up in the formula for the variance of y. Yi hat is going to incorporate some other sort of information that gives me a different fitted value for each observation, hence the subscript. Okay. So yi minus yi hat, that's my error. I square them, I add them up, I divide by how many there were, and sure enough, this part inside the radical looks like mean squared error. There may be something to say here about the distinction between dividing by n and dividing by n minus k. Just like the previous question where we had the option to choose between adjusted R-squared and regular R-squared, well, both of those formulas can be represented in a way that includes basically this part inside of the radical here in question 2, which is the mean squared error. But adjusted R-squared would have a little 1 over n minus k in that version of the formula, and I'd compare it with a regular R-squared that has the regular 1 over n in that version of the formula. When we talk about mean squared error that doesn't have a degrees of freedom correction built into it, this is the usual formula for mean squared error. Here, this stuff inside the radical. But the radical is here. I'm looking at the square root of the mean squared error. This is root mean squared error. Okay, which again has the formula for the thing in the name. Root mean squared error. All right, so it's not just mean squared error, it's root mean squared error. I'm hitting false down here. It would also be the formula for the standard error of regression that you see in Excel in the regression output table if I had n minus k here in the denominator. Just like different flavors of ice cream, just like different flavors of R-squared, a lot of statistics come with a degrees of freedom correction as an option. But here we go. Regular, old-fashioned root mean squared error. That's what that is. So I'm going for false. Question 3. A 95% confidence interval based on the normal distribution has upper and lower bounds equal to the point estimate plus or minus 2.96 standard errors. So in a normal distribution, 95% of observations are going to be within 1.96 standard deviations, or in this case, standard errors, if we're talking about the distribution of a statistic and we're using that terminology, away from the true average. Well, okay, but I see a 2.96 here. So as long as you didn't read it too quickly and think you see a 1.96, that was a trick right there. It should be 1.96. I'm going for false. Of course, if it was a t-distribution, I'd be looking for a larger number here. Again, I'd be looking for a larger number because of some sort of a conversation about whether I should have a finite sample correction, meaning something like a degrees of freedom adjustment. And if I have few degrees of freedom, the t-distribution is going to be a little bit different, or perhaps quite a bit different from a normal distribution. But as long as I have a large sample, the difference will be small. And as the data gets larger and larger, say 1,000 observations or more, I should be looking again at a number like 1.96, but not 2.96. That one's false. All right. Data entry errors can create outliers in a data set. Well, that doesn't seem like a trick question. That seems like a bit of a gimme. I'm going for true. Yes, of course, data entry errors can create outliers in a data set. Just imagine you're typing in a number that has a decimal place in it and you accidentally, using the number pad, fudge the decimal point and you wind up typing 1,000 instead of 1.000. Well, that's an outlier now. That's a very large, strange observation. So be careful with that sort of thing. The p-value for statistical significance of a regression coefficient may change if the model is changed to add another variable. Well, anytime I change the model, and it does say regression, so we're looking at regression models, but anytime I change the model in terms of changing what's on the right-hand side, or in a rather extreme scenario, perhaps changing what's on the left-hand side and looking at a transformed version of the variable y, which we can do, but we're starting from scratch with a whole new model. I'm going to wind up with different coefficients. They're going to have different standard errors. I'm going to have different t-statistics, and the different t-statistics are going to have different p-values associated with them. Yeah, all of those things are going to change. It may change. Question 6. An exponential smoothing model, okay, exponential smoothing produces some sort of an average of the last observation and the forecast that you made for the last observation and recombines those in a weighted average in order to predict the next forecast. So it's kind of a cute model, but let's see what this question says. Is produced by regressing a time series on dummy variables corresponding to each point in time. Well, I don't know what that is, each point in time. We've got the seasonal model where I would have dummy variables for each season, something like the first month or the second month of the year, or maybe different quarters of the year. Dummy variables corresponding to each point in time. I don't know what that is, but I know it's not exponential smoothing. I'm hitting false. 7. The regression coefficient on an explanatory variable may change when the model is changed to add another variable. Well, it's the same as that other question. Will the coefficient change when you add another variable to the model? Absolutely. Don't expect it to be the same. Maybe it'll be close, but it should change. 8. The best regression model is always the model with the lowest mean squared error. Ooh. Now, this one could be a bit spooky. The best regression model is always the model with the lowest mean squared error. Where have I seen a warning about this before? The lowest mean squared error for regression models, if I think about adding more variables to the right-hand side of the model, adding more variables will always make the mean squared error smaller, at least as long as I'm looking at this formula, right? The version of mean squared error inside the radical here is the same thing that shows up in the formula for regular r squared. It does not incorporate a degrees of freedom correction. Now, there may be something to say about even using adjusted r squared, where I have a version of the mean squared error formula that has a degrees of freedom correction baked into it, corrected mean squared error, n minus k in the denominator for the averaging part. That still may not be good enough. So this is, you know what? The mean squared error is a tool that you can use to try to compare things. A corrected mean squared error or adjusted r squared. There are many different ways that you could try to compare models, but that is not going to be foolproof. So even if I had a degrees of freedom correction in the denominator, I would still say false to this question. All right, just one tool that might be helpful, not guaranteed. Question 9. Like r squared, mean squared error can be used to choose between regression models. Yep, we were just talking about this. However, this model selection method tends to choose large models that may perform poorly out of sample. Yes, absolutely. Exactly like r squared, regular r squared. Mean squared error without a degrees of freedom correction is always going to improve when you have a larger model. Well, large models tend to perform really, really bad out of sample. And you can take this to the extreme and have a really, really, really large model that overfits the data and gives you an R-squared something like 0.999, and you can make the mean squared error as small as you want, and that model will almost certainly be terrible when you try to forecast out of sample or far out of sample. So we have this whole philosophy about choosing parsimonious models, smaller models, when we try to predict outside of the data set. And that philosophy goes with us everywhere. So I am going to press X to doubt, and I am not going to go with that. I'm going to say, oh, I'm not going to go with using this method. I am going to go with this comment here. However, this model selection method tends to choose large models that may perform poorly out of sample. That is absolutely correct. So true. 10, when adding an additional variable to a regression model, R squared always increases. Yep. When adding an additional variable to a regression model, mean squared error always decreases. Yep. It's the same information. When testing the significance of a model parameter using a t-statistic, we reject the null hypothesis at the alpha level of significance if the p-value is less than alpha. Actually, I'm going to pause. I'm going to zip back to 11 and just make a comment here. When we talk about mean squared error, because I expect to get this question, when we talk about mean squared error, typically this terminology, MSE, is referring to a formula that looks like this one inside the radical. Ignore the square root part. That would be root mean squared error. This with the 1 over n, not 1 over n minus k. That would be traditionally called mean squared error. And even though the terminology is a little bit loose, and the version that says n minus k in the denominator here is floating around everywhere, and that's the version that Excel produces in the ANOVA table. It would say n minus k in the denominator. Well, Excel does that in that table, but generally when we talk about mean squared error, we're just saying 1 over n here. That is the normal usage of that terminology. Or when I say normal, I mean the most common usage of that terminology. Sometimes I try to be extra clear and say uncorrected mean squared error and corrected mean squared error so that I'm absolutely crystal clear about which one we're referring to here. But when it says MSE, we're talking about the one that generally doesn't have a degrees of freedom correction. Okay, so yes, that's true. 12, testing the significance of a model parameter using a t-statistic. We reject the null hypothesis at the alpha level of significance. All right, alpha level of significance would be 1 minus alpha level of confidence. So I'm doing something like 95% confidence or something like 5% significance. I reject the null hypothesis if the p-value is less than alpha. Alpha is the small number. I want to see a p-value like 0.0000 less than alpha. Yes, yes, this is true. Question 13. All right. Somebody got some different font carried away with the copy-paste here. You are presented with the following partial regression output from Excel. The model estimates weight lost. You have this data set. You might recognize this example. The model estimates weight lost in pounds as a function of a workout program participants' starting weight and number of workout sessions. And this is kind of cool. So we see that the people who go to more sessions during this weight loss program, standard error, t-statistic, it's statistically significant. They lose more weight on average. So the people who are working out more lose more weight. Makes sense. We also see, again, weight, coefficient, standard error, t-statistic, p-value. Ooh, we see that the people who weigh more at the start, it's a positive coefficient. It is not statistically significant at the 95% level. This is just over 0.05, the 95% level of confidence. Now, it's dangerously close, and this is kind of a cool example because look at the t-stat, 1.99. This is a case where the small sample, 1.99 is more than 1.96, but because we're looking at a t-distribution here, I actually need to see a bigger number than 1.96. It's a little bit more than that, and you can see here, I've got a special case. 1.99 is not quite good enough for 95% confidence. I would be looking for something like 2.02, maybe, with this many degrees of freedom, 37 degrees of freedom. Okay, but it doesn't ask anything about the story yet. It says how many observations were in the data set. Type your answer in the box below. Here in the ANOVA table for Excel is the denominator you would find if you were using the regular formula for sample variance with this sum of squared variation, which is the numerator for variance, in the variable y. So this number divided by this number would be the sum of all the yi minus y bar squared divided by n minus 1. This number is the sum of squared residuals from the model, and what it would produce here as the corrected mean squared error would divide this number by n minus k. And this is k minus 1, which is sort of the difference between these two. It's how many additional parameters the model had, and that goes into the formula for the F statistic. We never use this number for much of anything else. But here I've got n minus 1 and n minus k. K here is 1, 2, 3 parameters that we estimated. So I've got 1, 2, 3, n minus 1, n was 40, and then if this is n minus 3, n was 40, all right? So 4, 0, that is the correct answer. All right, but you'll notice the formula Excel uses for mean squared error is the corrected mean squared error. And it doesn't actually call it, they're subtle about this, it doesn't actually call it mean squared error, it calls it mean squared residuals. I see. So mean squared residuals, maybe they changed the terminology there to be a little bit more clear that they are dividing by n minus k. It all makes sense. What are the model degrees of freedom for the regression shown above? Okay, so I had 40 observations in the model. I estimated 3 parameters. Degrees of freedom are n minus k. That's this, right? Degrees of freedom for the regression model is actually the residual degrees of freedom. In Excel's parlance, it's 37. 37. Okay. For a given number of sessions attended, and I'll qualify again, the 2 here is a number that we almost never use, right? For a given number of sessions attended, does the average participant lose more weight if they had a higher starting weight at the 90% level of confidence? Oh, look what we did. 90% confidence. So I go back up here. Higher starting weight, on average, positive coefficient. Is it statistically significant at the 90% level of confidence? And that is statistically significant, yes, at the 90% level of confidence. Doing a two-sided test here, I would say, all right, I've got something less than 0.1. So, yeah, they do, in fact. For a given starting weight, do study participants lose more weight if they attended more sessions? Use the 99% level of confidence. All right, so now we want to be absolutely sure. Okay, sessions, coefficient, standard error, t-statistic, and I've got a p-value. I need 99% confidence, so I need my p-value to be less than 0.01. Is it? Yes, it's 9.42 times 10 to the minus 5, which is pretty small. 10 to the minus 2 would be 0.01, so this thing is 3 orders of magnitude. Well, it's 9, so it's 2 orders of magnitude smaller than that. It's very significant. Okay. Do study participants lose more weight if they attend more sessions? Yes. I would reject the null hypothesis that they don't lose more weight. The maximum number of workout sessions a participant in this weight loss program attended was 8 sessions. Would you use this model to predict weight loss for someone who used these workout plans to work out twice a week for 2 years, totaling 104 workout sessions? Why or why not? Now that's a fascinating question because it's sort of like a forecasting question, but it's interpreting the regression model and the coefficient from the regression model rather than trying to just predict the outcome. Well, it's the same as when I predict the outcome using a particular value of something like t in a forecasting model. I'm plugging in a value, 104, for the number of sessions, and I'm extrapolating out of the sample. So you could look at this and say, that's not really a time series. Is everything we just learned about forecasting models with time series still applicable if we sort of go backwards and look at it in the regular cross-sectional regression context? And if your gut feeling is telling you that this is probably a bad idea, based on what we just did with some time series, you would be correct. All of those same ideas are still in place here. I'm forecasting in a way. I'm predicting. When we say forecasting, we're usually talking about the time dimension and looking into the future. But predictive analytics are exactly the same. I'm predicting what will happen for somebody who goes to the gym 104 times, twice a week for 2 years. So I just clicked an answer by accident, but let's read what these two things say and see which one makes sense. The first one says, yes, the model predicts that this person will lose 343 pounds after 104 sessions. Now, let me check and see if that's... Okay, sessions, take this number, multiply it by 104, and you'll get something like 343 pounds, which is completely reasonable. You might want to think about that twice. Is the average person going to lose 343 pounds? I don't think the average person has 343 pounds to lose. It's possible that the people in this sample were initially very, very, very heavy, and perhaps they did have 343 pounds to lose. And if you're laughing, well, it seems like that could be pretty extreme, okay? Well, imagine if we make this question even a little bit crazier. So instead of 104 workout sessions over 2 years, let's make it something like 6 years, and then we'll have 312 workout sessions. All right. Then you're going to lose over 1,000 pounds. At some point, this simply doesn't make sense to try to extrapolate. You should have doubt about stepping far, far out into, it is actually the future in this case because of the way we told the story, but you should have doubt about stepping far, far out in any direction, whether it's the future or along the axis of one of these variables that you've got in the model. I just don't think that this model is going to be good for forecasting so far out of the sample. No one did more than 8 sessions. So forecasting or predicting out to what would happen after 104 workout sessions, even though it's not time series, I think we know that's it. A linear model is going to forecast poorly this far out of sample. Yep, no matter what you do, trying to make a prediction that far out when I only have data about people from, say, 0 to 8 sessions, trying to predict this is going to be trouble. So let's avoid that. Okay, 18 is also really interesting. Determine what a curveball question. Determine whether the plot below comes from a cross-sectional data set or a time series, assuming that the horizontal axis represents the index variable. Now you might just look at it and check your instincts and say, this looks like the scatter plots we saw with cross sections. It doesn't look like a line diagram or any of the things that we saw with time series. So why does it not look like what we see with time series? Well, if this horizontal axis is the index, which would either be I or T, depending on the answer, this horizontal axis, if it was a time series, I should hope to see observations every day or every month, evenly spaced from left to right, one observation for each value as I move left to right. Look at the dots on this regression fitted line. I should see observations about this frequently. Well, I have an observation here and an observation here, and then I have a great big space where there are no observations. That seems troublesome. If this was a time series, this means that I either failed to collect a bunch of days or months of data, or some other weird thing happened. And then I have 2 observations that seem to have the same x value here. So if they do in fact have the same x value, they were both recorded on the same day. That doesn't seem possible. What about up here? These seem to have the same x value. And there might be others. These might have the same x value. It doesn't, oh, and so do these. So it doesn't look like this could possibly be a time series since there are these gaps and there are multiple observations at the same point in time, but that doesn't bother me as far as whether it could be a cross-section. You could have many people who have the same x variables, the same years of education, or the same distance traveled to an event. I'm thinking this is a cross-section. It doesn't look like a line plot. It doesn't look like a time series story. It looks like a scatter plot from a cross-section. This looks like a time series, and sure enough, we can see the horizontal axis label. It is a time series. This data appears to contain a seasonal component, question mark? I'm going for true. I see some wibble wobble here, some sinusoidal, not necessarily sinusoidal, but it's a fun word. I see some shape to it where it has a periodic up and down. Yeah, I'd go for that. Looks like seasonality to me, along with a trend. It seems to, if you drew a line and said, here's your trend line, it seems to have a seasonal bump shape around that trend line. So yeah, okay, I see it. The data in the previous question appears to contain a trend. Yes, sure, I'm with you. And 21. This is going to be harder, isn't it? Using only the graph, which model seems reasonable? Trend plus seasonality. I don't see a linear trend. I see something that could be maybe cubic. It goes up and then down and then it looks like it goes up again. But this doesn't look like any of those deterministic trend models. It has too much movement, and it doesn't seem like it has a direction, a particular direction that it wants to go at any point in time. This looks like stock returns. It looks like, well, it looks like a lot of time series data, to be quite frank. I don't see a trend, and I don't see seasonality. I don't see a quadratic trend. It doesn't have a happy face or a sad face. I don't know what regression on a binary variable is supposed to do in this category. The regression on a binary variable would give us two different fitted values depending on whether the right-hand side variable was 0 or 1. So for instance, it would separate all of the data into men and women, or people who have a bachelor's degree and people who don't. But this doesn't look like I can separate the data into two categories. The left half and the right half look like different eras, to be sure, but there's no clean break there. It seems wrong. Exponential smoothing, like the moving average and autoregressive models, exponential smoothing is designed to fit data that looks like this, that seems to wander on its own accord. I'm going for that one in this question. When testing for a seasonal component in the data from the previous question, yeah, we could. I mean, May, September, January, we could try. You fail to reject the null hypothesis that the differences between seasons are 0. Go figure. Which is the best explanation? This one also is fun. So, best explanation. It's not which one's a good explanation, it's not which one's a bad explanation, but let's read from top to bottom. I've got them in order here, more or less. If there is a seasonal component, oh nope, I don't have them in order. I've got the best one right here. If there is spoiler, if there is a seasonal component, it is too small relative to other variation in the data to be detected in a sample this size. Oh, that is exactly what it means when you fail to reject the null hypothesis. That just means that whatever the coefficient is, it's not larger than some number of standard errors that you would, 1.96 perhaps, that you would need for a certain level of confidence. Well, imagine that the seasonal effect is really, really small, and you have a small sample size, so you have large standard errors. If the true seasonal effect, let alone the seasonal effect that you estimate, if the seasonal effect is small and your standard errors are large relative to that, and you get a small t statistic, you're not going to find anything. So there may, in fact, be a seasonal component. It's just too small relative to the variation in the data to be detected in a sample this size. We're basically saying if you want to find a seasonal component and it's that small, you're going to need more data. Contrast that with this option. If there is a seasonal component, it must not be related to the time variable. That seems like nonsense. Contrast that with this. There is no seasonal component. Well, there might be. It might just be really small and we can't detect it. And it is not clear how to define seasons in data of this type. I seriously doubt that. I've got dates, right? It looks like September, January, May. I've got years. So this looks like monthly data, to be honest. This seems like evenly spaced. I'm thinking, it doesn't tell us, but boy, this looks like monthly data to me. I'm thinking it should be easy to define either 12 months or 3 quarters or perhaps some other form of seasonality if I want to get creative. There could be multiple options, but I don't think that would be a challenge at all. Wow, 30 minutes of talking. Pretty good. Question 23. While studying compensation at a large regional firm, N equals 833 employees, you can use your own judgment for whether you think that's large. You produce the following regression table. The dependent variable is earnings in dollars per hour. Right-hand side variables include average hours worked per week and tenure, defined as years working at this firm. Okay, so what do I see? Dependent variable is earnings dollars per hour. So the people who work more hours, of course you get paid more if you work more hours and you're being paid by the hour. But I see that the people who work more hours, not only do they get paid for more hours, they have on average a higher hourly wage. So the people with high wages tend to work longer hours, and the people working for low wages tend to work fewer hours or might be part-time. That kind of makes sense. I'm not super surprised by that. I also see that the people who have been with the company for longer make more money on average. This also makes sense. So both of these are positive coefficients, and they're statistically significant. I've got tiny p-values for both of them, large-ish t-statistics, 833 observations, plenty of degrees of freedom. You can see, for instance, that the difference between the r-squared, which is tiny, and the adjusted r-squared is not huge. If you round these, they both say that this model explains about 4% of the data variation. So, okay, doesn't explain much, but very significant effects for hours and tenure. Which is false? On average, controlling for hours worked, employees who have been at this firm longer are paid more per hour. Controlling for hours worked, that's correct. Employees who've been at the firm longer are paid more per hour. Positive coefficient, statistically significant. This seems true. Let's try the next one. Tenure and hours together explain about 4% of the variation in earnings across workers. Tenure and hours together explain about 4% of the variation in earnings across workers. Yeah, okay, that seems fine. Let's try this one. On average, controlling for tenure, employees who are paid more on an hourly basis work more hours. Ooh, look what they did there. Instead of saying employees who work more hours are paid more on an hourly basis, they said employees who are paid more on an hourly basis work more hours. Now, that is still technically true because the correlation is the same regardless of which variable you are looking at. It's just a little bit sneaky the way that phrasing is backwards from how you would normally interpret this coefficient, because the units on this coefficient say how many additional dollars you are expected to be paid based on the number of hours that you work. So the units have this story backwards. But if I flip the data, correlation is correlation, and statistical significance is there. So this one's actually okay, just sort of sneaky. And then tenure is not significant at the 0.01 level. Okay, so I guess alpha is 0.01. I went 99% confidence. And you know what? Tenure is very significant at that level. Okay. I was getting scared, but this is the one. That is false. And then to 24, regarding the regression result above, which of the following is true? All right, 3 options. A typical employee earns about $1.82 more or less than this model predicts. A typical employee, look at the standard error of regression. It's $11.82. So this is something like the average error term is $11.82. So typical employees' earnings in dollars per hour, their wage, is $11.82 above or below this model. So that 182 looks like a typo, right? That is actually false. How about tenure and hours are jointly insignificant at the 99% level of confidence? Ooh. Well, I've got a p-value here that says tenure and hours are jointly very, very significant. because this is 1.66 times 10 to the minus 8. So that's a number so small, I'm not going to bother assigning a level of significance to it. They're very significant. So this one is false. And how about the third option? If the goal is to understand the variation in earnings, the researcher should look for other variables, as these variables explain only a small amount of the variation in the data. Hey, that's great. If your goal is to understand why some people are getting paid more and some people are getting paid less, you haven't got much figured out just by running this regression. I did find that people who work more hours get paid more, and people who have more tenure at the company get paid more. And you know what? Both of those make perfect sense. But I've also found that 96% of the variation in how much people get paid was not explained by hours or tenure. So this model actually tells me very little about the overall variation in salaries at this firm. If my goal was to understand why some people get paid a lot and some people get paid less, this model didn't tell me very much. It only told me 4%. So I would say the researcher should look for other variables, as these variables explain only a small amount of the variation in the data. That's pretty good. That's an excellent conclusion. If this was your study and you collected this data because the boss asked you to do a little bit of research and find out what this looked like, one of the conclusions you might draw at the end of that study would be, you know what, this is the data that we had that we were able to correlate with the wages that we're paying people. And these factors really don't have much to do with it. We need to go back to the drawing board if we want to do another study, come up with some other variables to include. So that's an excellent conclusion. I'll say true for that one for sure. In your own words, interpret the coefficient on hours. Well, we sort of already did. For each additional hour worked, this model predicts an extra 15.8 cents per hour. 1 point extra credit. In your own words, explain the 95% confidence interval for hours. Okay, well, it's a confidence interval for hours. 95% confidence interval. This is the set of values that are close enough to my estimated coefficient that if I gave you a null hypothesis in this range, I would fail to reject that null hypothesis at the 95% level of confidence. In other words, this set of values is the coefficient plus or minus. It's actually the t-critical value. So it's not 1.96 standard errors. It's perhaps a little bit more than 1.96 standard errors, but it's pretty close to that. This range, minimum to maximum, is the coefficient here plus or minus a little bit more than 1.96 standard errors. So anything in this range I would fail to reject if you told me you thought that was the true coefficient. All right, I kind of just answered a couple of different ways. See if you can splice together a one-sentence version of what I just said, or use your own words. For questions like these, try to do it with one sentence. If you need to try a couple of different ways of saying it to get the one that you're comfortable with, you have options. There's more than one way to do it. And then same thing here. In your own words, explain the t-statistic for hours. Oh, t-statistics are easy. T-statistic for hours, right here. This t-statistic says this estimated coefficient is 3.73 standard errors above 0. That's exactly what it says. And that would be a perfectly valid answer by itself right there. Now, the next logical step is we notice that something being 3.73 standard errors above 0, if 0 was the truth here. It just never happens. That's kind of rare. So how rare is 3.73 would be the next question. But the question says, interpret the t-statistic, and the t-statistic tells me quite plainly, this coefficient is 3.73 standard errors away from 0. So that's the answer. Okay, study well. Good luck. Try the practice exam again. See if you can forget everything I just said and try it on your own. And study as well as you can. So I'll end the video here.